Hi everyone, with this video we begin chapter 10. It's titled Chemical Bonding 1, Molecular Geometry and Hybridization of Atomic Orbitals. This chapter touches upon the shapes of molecules and how important that is to chemical reactions. We're going to learn about the Vesper Model and examine the roles of chemical bonds and lone pairs on the geometry of a molecule. Alright, let's get started. By now, we know that molecular geometry is a 3D thing. It's not something that you just write on a piece of paper. A molecule's geometry affects all kinds of properties of that molecule, physical and chemical, such as melting point, boiling point, density, etc. The Vesper model, which stands for valence shell electron pair repulsion, helps us predict the geometry, the 3D geometry of the molecule from electrostatic repulsion between electrons, bonding and non-bonding pairs. This model is basically a simple procedure that we can do that will help us predict the overall geometry of a molecule or ion if we know the number of electrons surrounding the central atom in its Lewis structure. The basis for this is that we assume that the electron pairs in the valence shell of the atom repel one another, which we know that already. In a covalent bond, a pair of electrons, which are called the bonding pair, because that's what covalent bonds do, they share electrons. Those electrons are responsible for holding two atoms together. But in a polyatomic molecule, where there are two or more bonds between the central atom and the surrounding atoms, the repulsion between these electrons in different bonding pairs causes them to remain as far as possible. Bottom line is that the geometry of a molecule ultimately will be whatever minimizes the repulsion between electrons. So here we have a general class of a molecule, which is AB2. A stands for the central atom. Okay, that's just what the book uses to signify a central atom. B is classifying the outside atoms. So if you have a general molecule, which is AB2, which means you have one central atom and then the B's are the ones on the outside, number of atoms bonded to the central atom will be 2, the number of lone pairs on the central atom is 0, then the arrangement that this molecule will obtain would be the one that you see right there. It's a linear geometry. And since that central atom doesn't have any lone pairs, the two outside atoms will be completely away from each other as far as possible. And what's the only geometry that would be a straight line. There's a couple of bookkeeping things that we need to talk about before we go deep into the Vesper model. So molecules geometry affects physical and chemical properties. We talked about that. The geometry assumed a minimized repulsion. We talked about that. For the Vesper model, this is one thing we have not talked about, is as far as electron pair repulsion, double and triple bonds can be treated like single bonds. Even though in reality they're larger, it doesn't matter. For the Vesper model and how to determine what geometry is best for this molecule, you treat the single and double bonds, you treat the double and triple bonds the same as single bonds. Okay, so I'm going to go through an example right now. This would be an example of a linear molecule, beryllium dichloride. If you notice, the central atom has two atoms around it that's being bonded to, and those chlorines have those lone pairs, but the central atom doesn't have any lone pairs. So those two chlorines are going to try to get away as far as possible from each other because of the electron repulsion. So now we go into the next one. This would be class AB3, which of course A is the central atom, and now that central atom has 3 atoms bonded to it. But again, the number of lone pairs on the central atom would be 0. The shape that this would take would be a trigonoplanar. Just what that means is it's a triangle on one plane. So an example of this could be something like boron trifluoride. Boron has no electrons left when it makes this molecule. Remember, this is one of the exceptions. And then, of course, fluorine has those lone pairs around it. So it's going to try to keep each of those fluorines as far as possible from each other. So the only shape that it could do that with would be this triangle type thing, but it's on the same plane. You got to think about it in 3D. The next one would be, okay, so now instead of having 3 bonded atoms to the central atom, let's try 4. Well, this would be like methane, CH4, right? So this would give a tetrahedral geometry. So something like that would be like methane, CH4, and that's what it would look like. And this goes on and on with obviously bigger number of atoms bonded to the central atom. This one would be a trigonal bipyramidal, which is of course no electrons on the central atom, but has 5 bonded atoms to it. So this would be a trigonal bipyramidal, okay? So this is a lot of, a phosphorus pentachloride would be an example of this, but this is basically memorization, okay? You have to learn these things by memorizing them. This would be an octahedral. This is of course a little bit more complex, and something like that would be sulfur hexafluoride, okay? And this is the table that you see in your chapter, which summarizes everything that we've just talked about. The only other thing that we need to talk about is now what happens when that central atom actually has a lone pair. I showed you methane, the first one on the left. It has no lone pairs on the carbon. But what if we had something like nitrogen instead of carbon, right? So now let's say nitrogen, it's bonded to 3 things, and then that central atom has a lone pair. Lone pairs repel way more than bonding pairs. Okay, that's a rule. So if you notice, look at the angles. The angle for carbon, since there's no lone pairs on the central atom, it's 109.5. But now if you, instead of having an H there, you put an electron pair on that nitrogen, it closes it up to 107.3. So that angle becomes smaller. Why? Because there's way more repulsion coming from that lone pair than there would be if it was from a bonding pair. And you could tell, look at the oxygen. This would be water. Water, if you did the Lewis structure for water, you would have that central atom bonded to 2 hydrogens, and then it would have 2 lone pairs on the oxygen. Look how the angle of the distance between those hydrogens decreases, and that's again because of electron pair repulsion. The next table that we would go over would be the ones that have a central atom bonded to a number of different outside atoms, but then with that central atom having a lone pair. So for example, the first one would be like AB2E, where E stands for number of lone pairs on that central atom. It would be something like sulfur dioxide. So you have A, which is your central atom, B, which is your surrounding atoms, and then E, 1 pair of electrons on that central atom. And then what shape that would take. This would take a bent shape because there's only 2 atoms connected to that central atom, and that electron pair on the top really repels those 2 oxygens down. Okay, because they want to get away from each other as much as possible. Another type would be if you have a central atom connected to 3 different atoms, and then that central atom has also 1 lone pair. This would be something like I just showed you, ammonia. Ammonia is NH3, but that nitrogen has that lone pair, so it's going to take a trigonal pyramidal shape. All right, so again, it's a lot of different shapes that you're being exposed to, but there is a table in chapter 10 which summarizes all of them, okay? And this would be an example of a bent molecular geometry. It does have the electron pair arrangement is a tetrahedral arrangement, but the actual molecule is bent, okay? So there's a little bit of a distinction there. How are the electrons arranged? And that would take a tetrahedral shape. But if you just look at the molecule takes a bent shape because of those 2 lone pairs on that oxygen. I know this is a lot of information, but this is all in your book, and it will be covered in your final, so I suggest that you take a glance at it and try to understand all of these different ones. And I'm going through them really fast through these slides, but basically what I want to do is I want to get to this. This is table 10.2 in your chapter, which basically shows you all of the possible shapes and arrangement of electron pairs in all of the molecules. Okay, so I would suggest looking at this and just, glancing them and doing a couple of problems to see if you can figure out what the electron pair arrangement would be and what the geometry. Remember the difference between if you have no lone pairs on the central atom, it's different. It's a little bit simpler. But if you do have lone pairs on the central atom, then it becomes a little bit, you got to do one more step. It's a little bit more complicated. So As far as what steps you do to figure out the molecular geometry, you would first draw the Lewis structure for the molecule, and then of course consider only electron pairs around the central atom. And then you would count the number of lone pairs on the central atom and number of atoms bonded to the central atom, and then use the Vesper model to predict the geometry of the molecule. And you can use the table to predict it for now. So you would draw the Lewis structure, find arrangement of the electron pairs, find the arrangement of the bonding pairs, and then determine the geometry. Alright, so this is a couple of problems that I wanted to do. So use the Vesper model to predict the geometry of the following molecules and ions. And this is example 10.1 in your book. So this is arsenic and 3 hydrogens. Arsenic has 5 valence electrons, and of course hydrogen has 3, because, well, 1, but you have 3 of them. So that means that you're going to have a total of 8 valence electrons that you have to account for. What goes in the middle would be your arsenic. Excuse my drawing, but you would have something like this. This takes care of 6 electrons, right? Because of those bonds that you've just made it. So now you only have 2 left. So you have this H, H, H like that, and then you have the 2 bonding pair, the 2 lone pairs are left. You put them on the arsenic. So now we can predict, okay, so there's a central atom, it's bonded to 3 atoms, but that central atom has a lone pair. What geometry would the molecule be? You would end up with a trigonal pyramidal geometry. If you look back at your table, that is a geometry that has 1 central atom with a lone pair and is bonded to 3 atoms. And that's exactly what we have here. Now, if I asked you what would be the arrangement of the electrons here, it would be more of a tetrahedral, because that lone pair is going to repel those hydrogens a little bit down. So you're going to have tetrahedral arrangement for your electrons. What I want you to do is try the rest of these on your own. Of course, B through E are in your book, but if you notice, I gave you some extra ones like phosphorus trichloride and nitrite. So I would like you to try those as well, because if you can do those, then you're in pretty good shape, I think, for your final. Alright, that's it for this video. Thank you guys for listening, and I'll talk to you later.